In game theory, we model decision-making as an optimization problem. We assume that for all of the problems we study, we can write down numerical utilities for all of the outcomes, and then predict behavior by calculating the decisions that will maximize that utility in expectation. And when you stop to think about it, that's a really strong assumption that we should totally be skeptical of, because nobody actually makes decisions that way, thinking about, if I go to the basketball game, that'll be worth 15 utility, but if I go to the soccer game, that will only get me 10. So modeling decisions in terms of utilities is clearly wrong. It doesn't describe what we actually do. But despite that, it can still be useful. So my goal in this video is to convince you that this makes sense at all, and under what conditions we can model decision makers as if they were maximizing an expected utility. And importantly, when we talk about numerical utilities, that's not the same as money or any other specific resource. And when we say that a player is maximizing their utility, we're not necessarily saying that player is entirely selfish. What we are saying is that for every possible outcome, the players can describe numerically how much they like it. But it's totally possible for the utility values they assign to take into account effects on other people. For example, when we described the TCP backoff game last time, we did assume that the players were selfish. When we came up with these utilities, the only thing we factored in was how much delay that user was personally experiencing. But if we think that one or both of the users wants to not be an asshole, and therefore is less happy when other users experience more congestion, we could modify the utilities in the payoff matrix to take that preference into account. Specifically, we could write down in our model different payoffs for the unselfish user that are lower in cases where other users are suffering from congestion. And this might still feel somewhat arbitrary, so we want to build up some additional justification, but the starting point should be about comparing outcomes. If we're going to model decision-making at all, we need some way of saying, I like this outcome better than that one, which leads us to the idea of a preference relation, which is just a formal way of writing down this sort of relationship. If I prefer outcome A over outcome B, then we can record that as A squiggly greater than or equal to B. And this might also seem like a really strange thing to define. So you could rightly ask, what's the point? Why is it better to start here than with utilities? And the key idea is that we're trying to assume as little as possible. When we say that a preference relation exists, all that means is, if I show you two outcomes, you are capable of picking between them. Do you prefer the outcome where the robot escapes, or the one where it's recaptured? If you were involved in this situation, you'd be able to make some decision between those outcomes. And we use a symbol that looks like greater than or equal to, because if you observe someone making choices, that's the kind of data you're going to get. If I see you considering Fruit Loops or Cheerios and selecting Fruit Loops, then I've learned that according to your preferences, the outcome Fruit Loops for breakfast this morning is at least as good as the outcome Cheerios for breakfast this morning. Of course, it's also possible to have preferences where you are indifferent between some outcomes, or where one thing is strictly better than another, but you can derive those relations from the basic one in the obvious way. For example, we can say that you're indifferent between two outcomes when the weak preference relation holds in both directions. So, armed with this idea of a relation that records a decision maker's preferences, I'd like to describe a few properties that a preference relation might have. As we'll see, collectively, these properties comprise the axioms of utility theory. And where we're going with this is that if a preference relation has all of these properties, then the decision maker whose preferences we're describing must be an expected utility maximizer. So as we go through each of these preference axioms, think about whether that property makes sense in terms of describing your preferences or those of some other decision maker. Our first axiom, completeness, just says that among the outcomes in our model, it's possible to make some comparison between each of them. Importantly, this is an inclusive OR. It's entirely okay to have A weakly preferred to B and B weakly preferred to A. That's just the case where you're indifferent. But if the preference relation is complete, it cannot be the case that there's some pair of outcomes that the decision maker is unable to compare. The transitive property just says that your preferences establish a consistent ordering. If you prefer A to B and B to C, then you also prefer A to C. And when we think about transitivity, it would be easy to come up with examples where we say, I prefer Fruit Loops to Cheerios, and I prefer Cheerios to Wheaties, but sometimes I pick Wheaties over Cheerios. And the weasel word there is sometimes. Your preferences could still be transitive if we specify the outcomes correctly. When I talked about cereal before, I said the outcome Fruit Loops for breakfast this morning is preferred to the outcome Cheerios for breakfast this morning. And so by carefully specifying what we mean by the outcome, the fact that you ended up eating Fruit Loops means that you didn't have this sort of circularity in your preferences. This morning, it's clear that Fruit Loops was the top choice. To talk about our next axiom, substitution, we first need a definition. So a lottery is just a randomization between different outcomes. For example, we could have a lottery that with 30% probability gives you Cheerios for breakfast this morning, with 20% probability gives you Fruit Loops, and with 50% probability gives you Wheaties. And so we'll extend our notion of preferences to say that you could also make decisions between different lotteries. If I showed you this lottery, and one that was a 50-50 randomization between Cheerios and Fruit Loops, you could tell me which one you prefer. And this lets us define substitution, which says that if you are indifferent between two outcomes, I can swap one for the other in any lottery, and that will make no difference. So if you're really indifferent between two outcomes, you should still be indifferent between them when you're only randomly getting them some of the time. But now that we've extended our idea of preferences to also talk about your decisions among lotteries, we need to go back and update completeness and transitivity. But the definitions are exactly the same. We're just saying that you could make a choice between any pair of lotteries, and your preferences over lotteries are transitive. The decomposition axiom says that if I make up some complicated lottery where I flip lots of coins and roll lots of dice, You don't actually care about the process by which I randomized. The only thing that matters to your preferences is what are the eventual outcomes and with what probability do they happen. So here I've specified a compound lottery, where in the first lottery that has probabilities p and 1 minus p, one of the outcomes is actually another lottery with probability q and 1 minus q. And decomposition says that you don't care about the fact that I did this lottery in 2 stages. You are indifferent between that and a 1-stage lottery with the same probabilities. And it also says that if you have a complicated lottery where the same outcome turns up on different branches, so let's suppose I modified this lottery to be just over A and B instead of A, B, and C, then you'd also be indifferent between these lotteries with 2 different ways of getting outcome B and another that combines them. Where here I've simply added up the total probability of all the different ways to get outcome B. Our next property is monotonicity, which is really just saying you prefer a higher probability of a good thing. So if you're comparing 2 lotteries over the same outcomes, the one that gives you a higher probability of the better outcome is preferable to the other. And the property is of course saying that this holds in general for any higher probability, not just 0.6 versus 0.5. Before we talk about the final property, it makes sense to pause and state a lemma that can be proven using only the first 5 axioms. And this lemma talks about 3 outcomes that, according to the preferences, are good, medium, and bad, and compares a lottery between the good and bad outcomes versus the middle outcome. So here we have 3 outcomes, good, medium, and bad, and we have strict preferences between them. Good is definitely better than medium, which is definitely better than bad. And then we're comparing a lottery between the good outcome and the bad outcome versus the middle outcome. And we could randomize between good and bad with different probabilities. If we set up the lottery so that the probability of the good outcome is 0, then this lottery is equivalent to the bad outcome, and so you would definitely prefer the middle one. And as we increase the probability of the good outcome away from 0, there will still be some region where you prefer the middle outcome over the lottery. But then at some point, there must be a switch where we go to preferring the lottery over the middle outcome, because by the time we get all the way to a probability of 1 on the left leg of this lottery, the lottery becomes equivalent to just the good outcome, which is definitely better than M. And so this lemma is just saying that as we increase the probability of the good outcome, there will be some tipping point where we go from preferring the middle outcome to now preferring the lottery. If we think about how would we show this lemma, you can probably convince yourself that we need completeness to say that we can compare the lotteries for any different probability. And transitivity lets us say that once we're on one side of the tipping point, everything else is going to be worse. But for now, I'll defer the details of proving this lemma and return to defining our last axiom. But the reason we took this diversion to state the lemma is that the continuity axiom talks specifically about this tipping point. And you'll notice that in the lemma, we're talking about probabilities below the tipping point and probabilities above the tipping point, and what that means for your preferences. But the lemma doesn't actually tell us what happens at that tipping point. And so the continuity axiom says that at the tipping point, you are indifferent between the lottery and the middle outcome. And we call this continuity because we're saying that there isn't some sort of discrete jump at the tipping point where we go from the lottery is strictly worse to the lottery is strictly better all of a sudden without having indifference in between. So that was an awful lot of defining of jargon, but the reason to go through all of these axioms is that when we put them together, we arrive at the von Neumann and Morgenstern utility theorem. And if you're curious, yes, this von Neumann, who helped to establish the foundational principles of game theory, is in fact the same von Neumann who later went on to establish some of the foundational principles of computer architecture. And what this theorem tells us is that a preference relation satisfies these 6 axioms if and only if there is a corresponding utility function where the decision maker always acts to maximize expected utility. We'll defer the details of this proof for now, but it has to show both directions. First, that if you're an expected utility maximizer, then your preferences satisfy these axioms. And that can be shown numerically, where if you start with a utility value for every outcome, then whenever you're faced with a decision between 2 outcomes or 2 lotteries, you'll be able to make a decision, and those decisions will be transitive, and so on. The other direction of the proof, showing that if your preferences satisfy these axioms, then you have some utility function that you're maximizing, works by figuring out the best and worst outcomes among all the available choices, and assigning them specific utility values, and then asking questions about your preferences to establish which lottery do you prefer, and use that to pin down the tipping point, and in so doing, figure out the utility value in between those extremes that works for all of the other outcomes. And it's possible to do that if your preferences behave according to these axioms. So what does all of this mean? Well, we began by questioning the idea of expected utility maximization as a way of modeling decision-making in game theory, because that doesn't feel like how we make decisions. But this theorem tells us that if our decision-making can be described by preferences that follow these 6 axioms, which at least to me seems a lot more plausible for how I make decisions, then there must be some utility function that is being maximized by my decisions. Now of note, this does not guarantee that the utility functions that we've written down for our examples so far are at all correct. And it doesn't even guarantee that we are all expected utility maximizers all of the time. You can absolutely come up with perfectly reasonable examples of decision-making that violates one or more of these axioms. but I hope this has given you some sense of why we are willing to use expected utility maximization as a core component of our modeling, and what assumptions we are making behind the scenes when we do expected utility maximization in game theory.